All right, so welcome to the very last session of the AMATIC Midwest. And our website is amatic.org/Midwest. And today we have Stewart Mitchell here, who is a student at Wayne State University and also one of my former students as well. And so Stewart will be talking about some projects and strategies and resources for teaching differential equations that could be used in a classroom in person and maybe even transfer over to the online setting if needed. So Stewart, I'll turn it over to you now.
Thank you for the introduction. Hi, everyone. As John said, my name is Stewart Mitchell. I'm a grad student now at Wayne State University. And I was just going to outline a few different layouts and ideas that I had from a project that I did when I was in my differential equations class. The project that I did, the origin, so to speak, was because I was part of the honors college in undergrad. I had to do the project as extra work. At the end of each chapter in our textbook, we had these like application assignments that covered topics like motion, physics, engineering, and stuff like that that related to differential equations, I guess, in real life. And I had to choose one because there were about 4 or 5 at the end of every chapter and complete it and then turn it in separately. And I did the project alone because I was the only one who was doing a project like that in my class at the time. But I think that has a lot of potential to be applied to a class-wide setting. Just to preface this, unfortunately, I don't have my project as a reference due to COVID. I had gotten in touch with my differential equations professor before COVID started to ask to get the project back so I could have some physical examples in here, but unfortunately the university shut down before I could get them. And as far as my textbook, it was a rental, so I don't have that on me either. So I just kind of going to be broadly talking about this, unfortunately, without any concrete example problems. But a lot of different textbooks have similar projects or similar application or problems or challenge problems that could be used in the same way. So my first idea was similar to the one I did and just have it as individual extra credit for students who elect to do so. So you'd execute this project similar to the original, make it extra credit, have any students who want extra credit complete one application assignment at the end of each chapter and then compile all of them over the course of the semester. And as far as scoring, I just say make it worth whatever a normal assignment, or make like it the normal amount of points that any assignment is. There would just be extra credit points. And depending on how many points are offered in the class, maybe cap it at like 4 or 5 assignments that they can do. Like they can get a maximum of say 50 points extra credit from doing like this this project on their own. Or if your class has a lot more points involved, you could make it worth more. But that it can be flexible depending on what kind of system you have. My second idea was just having it as like a regular recurring group work. So have students break into, different groups of 4 to 5 students each time, or potentially larger if you have a really big class. Have the groups choose an application assignment at the end of the chapter, and then complete it as normal coursework. So score it how you would for, either participation or another assignment. But that way, you have students, working with everyone in the class at some point. You have them thinking beyond just, the normal lectures. You have them thinking about real life applications, which is important. I know that I was one of the only math majors in my differential equations class. The majority were, either going to be physics majors or engineering, a lot of engineering majors especially. So I think that having them complete these extra projects would have been beneficial just for from an application standpoint for them too. So it would have put them more in their own field. And as far as the group work goes, when I was working for John, starting in the fall 2018 semester, which was actually concurrently to the project that I was doing when I was taking differential equations, he split students into different groups every class period to work on group work, and it really seemed to help them because at that point we both could move around the classroom and help students in groups, because not every group has the same question. Then if certain groups finish first, they can help other students, and also make students form relationships with each other, so that they can help each other too, and it just fosters more of a sense of community in the class. So in addition to helping them think more critically, it can also give them some friendships or even just some like allyships in the class, for help if they don't have anywhere else to turn as far as for asking questions. So my third idea was having it as a final project or a term project. In this case, either my idea for this was either have students do it individually or have them break into really small groups. To do this because if you have a larger class, it'd be kind of tedious and painful to have to grade each individual student's final project that involved one application assignment from every single chapter. But in this case, if they were in groups, I would say have them choose 2 application assignments from the end of each chapter, since they are in groups and it's a larger project, and then compile them at the end of the semester and have it count as 10% or so of their grade, a pretty significant chunk, as you would like a term paper or something. But that would be a little bit more formal, and carry a little bit more weight if that's what you were looking for. Because I know, I'm sorry, I don't know where I was going with that thought. But that'd be a little bit more to go with that. And actually, I was just thinking about this a little bit ago. I have one more idea, and have it as you could have these application assignments as class discussions, because you could discuss an application problem as a class at the end of each chapter to check students' understanding. If there are any gaps in understanding, they could be filled in. You could even have students break into groups and work on these just as a discussion time, or just kind of as participation points, and go around and see if they have any questions, see where they're kind of falling short in their understanding of the problems, and it could kind of mitigate the misunderstandings that could happen before exams, or just overall, so that where their understanding's at. As far as resources, the only resource that I used for this for the project that I did was the textbook we had, Fundamentals of Differential Equations by Nagel, Saff, and Snyder. Even if that's not the textbook you're using, but you saw it and you liked the projects, you could potentially just photocopy the projects and hand them out as like an assignment in class, or think about using those. The only downside is it does cost money. But earlier on this year, John and I compiled open education resources, and we found differential equations. There's some textbooks, there's videos, there's resources, and then notes. So that textbook has some material that could be used too if you didn't want to purchase a textbook. And then one last thing in this presentation before I kind of turn it over to where we can all talk about more, more of the specifics, or if any of you have any suggestions for how it could be made better, or have any extra added ideas for formats. There's online learning resources that John provided from Semiode, where they are promoting just a course for how to teach differential equations online. and give some resources for teaching differential equations online for students and educators. So I think that might be worth looking at, just because it's a very trying time right now, and I know differential equations seemed difficult enough to learn in person in classroom setting, let alone online. So I think that this could be beneficial. Right, hold on, let me. And thank you for listening. One second.
Stewart, have you had a chance to look at any of the Simiode resources, the materials that are there?
I haven't yet, because I just got those sent to me a little bit before this presentation, so I didn't have a chance to look through them too much.
They're really cool. There's some really good stuff, and what I like in there is something that your ideas were sort of kind of headed towards was the more you incorporate these projects into what you're doing in the classroom, the more your teaching is going to change.
Yeah.
Because you find yourself kind of orienting yourself towards these, and that's going to affect how you approach the actual teaching of the subject.
Oh yeah, for sure.
I find myself changing how I'm doing things. The more kind of, I call them tasks or investigations. I don't call them projects, but the more of those that I assign, the more it's changing the way I teach the class. It's really cool.
Yeah.
It's a lot of fun.
Yeah. No, I definitely I really liked doing that as part of the class. I think it added a lot for me. It helped me understand the material more as I was going along, because I actually had to apply it rather than just use it for our normal homework problems. So that definitely helped. And I think that got me thinking even back then, this could be something really beneficial to do if I have to teach this one day, or just for other educators who who could get use from it. And once again, I apologize for not having the actual resources with me here. Kind of got derailed by COVID. I was hoping to have some physical examples from what I had done in the past, but unfortunately the projects are still sitting in an office at Wayne State.
Can you describe them at all in terms of what the particular topics were? I'm curious.
It was quite a while ago, and unfortunately I don't have it. I know most of the topics were just kind of physics application problems. I know one of them was about a hypothetical gravity train. One was about modeling snowfall. One was about
was that the snowplow problem?
Yeah, the snowplow problem. Yeah, that was one of them. One of them was something about uniform motion. So stuff like that, a lot of physics, a lot of engineering, or just kind of modeling situations with differential equations. I know one, I think it was about the population of, I want to say meerkats or something like that. So it was just, it was a lot of either modeling or physics or engineering application problems.
Got it. Cool. Well, thanks for sharing. I enjoyed it.
Yeah, so I can comment sort of I kind of had Stewart put that slide about the Simiode remote teaching modules in the slides at the last minute, because I just got that email last week or something. But so excuse me. So I learned about Simiode because I was at Math Fest a couple of years ago, and Brian, the Simiode director, for some reason, was standing right in line with me at the Starbucks, and he just wouldn't stop talking to me. And so if you know Brian at all, he's that person that will just tell you everything about Simiode ever to anyone, even if you really don't want to know. And so then he invited me to the summer workshops, and so I went to the summer workshop a couple of summers ago. They have one for people who are new to teaching differential equations, and then they have one for people who want to become like actual writers of these application scenarios. And so I went to the beginners one, and of course, like he had already encouraged me to go to the writers group, but I haven't even written one yet. So you want me to go to the writers group immediately? And so I went to the beginners group, and I actually wrote a module during that beginners workshop, and uh, I now like use it for like introducing like basic terminology and things like that in Calc 1 when you like do basic differential equations in Calc 1. But I'm sure that like differential equation students would like the scenario because I stopped it at the part where the Calc 1 students would actually not be able to go much further. And so I got this from a larger research paper that I had modified. And so I just pulled certain pieces from it, and then Brian says, "Oh, you should publish it as a scenario in Semiode." And I'm like, "Okay, well, I probably will at some point," but I didn't do that yet. I did present it at their special Semiode session at MathFest last year, and I was supposed to go to their module writers group this summer, but that all got foiled. And so I'm really like happy that they are like doing these remote learning modules, because these are really like the same things that I would want students to sort of work through in small groups, or like guide it with me working through them with them. But now there's some that lecture portion is all that minimal lecture portion, because these are all scenarios they're supposed to work through on their own, are all like going to be online so that they can self-guide through this online learning environment. And so I think that this is a fascinating idea, and part of my goal for when I was going to teach differential equations the next time, which of course every class is being scrutinized right now again to see if it should even be offered online, but was to teach it with a more modeling, or a more maybe like even some simulations in it. And I had a hard time even thinking about how that would be done because of like on-campus restrictions, like is there a computer lab that will seat 35 people during the time that we have class? Well, now that I'll be online, I guess I don't have to necessarily worry about that. Like I might be able to take a few more risks in terms of the students actually working on modeling, or things like that that would require a computer to do simulation. So I guess I'm wondering from Stewart, from your perspective of being somebody who was assigned one of these projects, I know yours was like an additional project in addition to the work that you already had, but I think that with the move online, like a mandatory project, or at least some problem solving small groups or something for all students isn't a bad idea. But I'm wondering, like, what would you recommend as the workload? Like, it's like, would you say that like it would be good to have a problem like a month, or maybe one problem where you try it at the end of the first month using the techniques you already know, then at the end of the second month you're assigned the same problem, but you see what else you know now that you could use to solve in a different way, and you keep on resolving it like every month until you get all the way through the class, or you think like there is a certain limit to how much like a student would be able to handle. And I had another question like similar to that, but just in terms of like your thoughts on from that perspective about the workload.
Yeah, I think that for online sense, especially for differential equations, it's kind of hard to implement. Like, it'd be good to make a project or assignment like this, like mandatory and not extra, and maybe, you know, like scale back on it a little, like maybe not do one for every single chapter, or just like you said, pick one and then see how you can solve it differently, or potentially even make, you know, like have students meet with each other in groups, like via Zoom or whatever other platform there is, and then like record their meeting of going through the problem, and then have them submit that in like a discussion board with other questions that they have about that, so that like the class can talk about it. And if they had, like, you know, they're really confused, you could see their playback of like what they were talking about and where they were getting derailed. But like, in terms of workload, I guess I wouldn't think you'd want to like put too much like extra, because it's already stressful enough for both instructors and students to be going online completely this semester, for everything, because that's not normally how it works. Did I answer all the questions that you had, or?
Yeah, I guess like if I guess if they're like our uh, oh yeah, I remember what my other question was. So like did you have any like use of like computer software in your class, or any use of simulation? And like, do you feel like if you did or didn't, that it uh, could be useful, and sort of in what ways?
I didn't personally, and that wasn't like, I guess, encouraged or really discussed, but I think definitely that would be really helpful, because, you know, I feel like the application of differential equations, especially in an engineering setting, is using software to model scenarios, like, or to model the equations or the system, so that you can observe what's happening. So I think that, you know, if there was some access to some kind of free software, or software that could be like provided by the college, that would be useful to like teach students how to use it, and have them plug stuff in scenarios where they would need to model a system with software, like for, you know, like a pendulum problem, or like or some kind of motion problem and stuff like that, so they can actually observe what's happening, because it might actually, you know, it might help them. Because I know for me, I had to just kind of think about it without seeing it, and like write down my thoughts, and then coordinate with my professor and ask her questions and stuff, and then come back and go from there. So I think that software would be useful.
So at my school, I haven't taught DiffyQ yet, but I hope to soon here. But I just always have stuff going on. But at my school, they actually build in a lab hour into the class, and so the class is typically taught in a computer lab, and 1 hour a week the students have a lab assignment, and we use MATLAB. I don't know if anybody uses that or not, but we use that in both our differential equations and our linear algebra class. And so they would do pendulum problems, or orbits, or again, I don't know, circuits, those types of things, but they do use some software, and they don't get it on a test or anything like that, but for projects, lab assignments, and then in the moved, I don't know if you guys have heard of this software, Octave, but it's a free software that students can download and install. And if you know MATLAB, the coding is basically all the same. So it's like a free version of MATLAB. And so that's what the instructors that are doing linear algebra and differential equations are doing for this online environment, is they're having students download this software, and then they can still learn, to use it. Because I'm in California, we have agreements with like our universities that students know how to code in MATLAB. So, and I put the link in the chat, by the way.
Yeah, thanks for that. I'm really surprised, Stuart, to hear that your differential equations class was not using computer software. I mean, I can't imagine teaching it now without it. I mean, I've been teaching it for about 6 years, and when I first started teaching it, I hadn't taught it in God, 15, 20 years. And in that time, the computer software had changed, and, I mean, just dramatic leaps and bounds. I mean, from the mid 90s, software was not too easy to find, and it was really expensive, and it was really a pain in the ass to use. And I used Maple early days, and also Mathematica, and those are pretty beefy. They can do lots of stuff, but the early versions of those were not exactly user friendly. But now we're using Maple all the time. It gets infused in, like I was saying earlier, it gets infused in the teaching practice. And wow, to not have that available, it's kind of like the metaphor I use is, it's like asking your students, okay, take your glasses off, okay, now go ahead and try to read the board and do your work. It's like, oh, that's terrible. Why would you do that to people?
In some like sections, my professor would show us like, I guess, videos of people using some of the software to like model what we were doing, but like never actually did it for like, in front of us, and we didn't have to.
It's like watching cooking shows with wonderful food, and you're just like, and do we ever get to try this? It's like, nope.
Yeah, no. So I mean, I think it would have been kind of nice because, like some in some of my higher level classes beyond that, they've like asked us if we knew how to use like Mathematica or MATLAB. I'm like, no one's ever shown us before. So like I can learn. It's just I've never had to. Because like I guess here they just don't care about coding as much, because like my when I was in my statistics class at Wayne State, we started using R, and that was the first time I had like used a software for a math class, and that wasn't even required. It was just something the professor's like, if you're moving on as a statistics major, you need to know how to use this, so I'm gonna show you how.
Or a scientist, or
just
anything.
anytime, and it's really useful. I've used it since then, sometimes just to work with data sets. Like it's nice to use, but like it would have been nice to know how, but we never got shown how to use any of that in my DiffQ class. We just kind of went through, I guess, normal lectures.
I found it's indispensable in terms of being able to do exploration. So to ask the question, hey, what happens to that, harmonic oscillator when we start changing these particular parameters? You can really fast throw up a phase plane and start looking at, what happens to the shape of the phase plane when you start changing these parameters around. And that's something that, I mean, when I was learning this stuff and computer software was just not there, you couldn't do that. And like you were saying, you just had to kind of imagine things. And if you didn't have somebody there to sort of like, not just help you, but guide you, like say, okay, now picture this. And now, no, don't think about that. Think about this. I mean, if you didn't have somebody there to do that, it would be really hard to, in your head, kind of follow that the model and try to visualize what's going on. That would be so hard to do. I'm really sorry for you that you had to do that. But the good news is that you're probably going to appreciate it so much more when you get to use that software later on.
Oh yeah, for sure. I mean, and like, I guess we just, our class wasn't very like application centric. It was very much just, here's this theory or theorem, here's like what you do to solve a problem like this. And then we didn't focus a lot on like models or application problems very much in the scope of what we were learning. So that's why it was really nice to have done that project, because I actually got to do some application work, even if my career path isn't going to be engineering or something like that. It was nice to know, like, hey, this is how you apply this in real life. You can model things with it in real life like this. This is an idea, like stuff like that. But yeah, the software definitely would have made it nicer if I would have been able to to take it and model some of those problems for myself, because like just for the exploration standpoint, like you said, because like I love using software for statistics because it was a good way to explore too. And like you didn't have to spend the time like doing all the nitty gritty that you already knew how to do. You could see what new things were happening and make draw new conclusions for yourself. But
I mean, I don't get to see a whole lot of math majors where we're at. We're a large supplier of future engineers, and so we a lot of my DiffyQ students, most of my DiffyQ students are engineers. Sometimes I get computer science people are interested, or physical sciences, but every once in a while I'll get a math major. And one of the things that I make sure to talk to them about, and the scientists for that matter, is if you think you're going to go into science or engineering, or if you think you're going to go into science or mathematics and not have to communicate with people who are in engineering and communicate with people who are in computer science, you got a rude awakening coming. And so you have to know how to communicate with people like that and what kind of software they're using. And so even from the standpoint of you as a future mathematician, you're going to be almost certainly teaching and or working with people who are not going to be mathematicians, right?
Well, that's kind of what I saw, because obviously, like, in my classes beyond differential equations, that's stuff like only math majors have to take. So I was with all math majors, but everything before that, the majority of the class was engineers. Even in my DiffyQ class especially, I'd say like we had a class of like 26 people and 23 of them were engineering students. There's one computer science student, I was the math major, and then I think someone else was in physics. I think they were a physics major.
Physics,
but
makes
like
sense,
other than that, like mostly engineers. So like the fact that even my professor didn't go through a lot of application was like astounding to me, because like the majority of your class aren't just going to do this for the theory, they're doing it for the application. Like
I think this is why a lot of my my students who are, future engineer types, that they're like working, on the weekends or day jobs, internships at engineering firms, and they come to me with stories of, oh, all the people where I work, they always say they don't need any calculus. They don't ever do calculus. I'm an engineer and I don't do calculus, and I'm like. If you think you're an engineer and you don't do calculus, then you don't understand calculus.
yeah.
Just because you're not like writing out derivatives by hand doesn't mean that you're not doing calculus. And so I take that as a charge as a math professor. I take that as a charge for, we have to find better ways to communicate with people and let them see how, differential equations isn't just, can you solve this, linear, non-homogeneous differential equation by hand? Can you use 3 different methods to solve it? It's also, what does it mean in the bigger sense? How does this all connect? That's a tough job, but I think it's an important job for us, because there's not a whole lot of mathematicians in the world, but there's a lot of people who need mathematics. So.
Oh yeah, for sure. Yeah, because my thought, I guess, kind of that I've kept in the back of my mind through, like, as soon as I decided that I wanted to pursue like being a math professor, that I've kept in the back of my mind through all my classes is like, I guess not as much so in like the higher level ones that I'm taking, because I won't really be teaching those, but mostly for like the calculus sequence, or like even before the calculus sequence, like how can I I guess make this like more inclusive to like different, like, you know, different uses, like what kind of real world examples can I throw in, like what kind of things can I do to appeal to, like, you know, the people who are going to use this just in their everyday life versus like engineers versus scientists versus, you know, whoever, like what kind of composition my classroom is depending on the class too. But like I've always thought about, you know, like how can I show people that this actually does apply to real life? It's not just learning it for nothing. Like, you know, people actually do use it.
Well, and
all the
so
time.
like I know that with like a not with differential equations, but with what was class was it? Like discrete math. A couple of years ago, one of my colleagues came over to me and said, uh, "You're teaching the class now." And I said, "What do you mean that I'm teaching the class now?" And he said, "Well, uh, I know that over the years, like the type of students in the class have changed, and they need an instructor who is more likely to incorporate applications into the classroom, and I'm not the person who's going to do that. So I'm having you teach discrete math from now on, because I think that you'll have some better ideas of some sort of applications that people might want to use." And I know that he was talking about like the particularly the combinations and permutations type sections, since I have a statistics background, and that's where a lot of that type of stuff occurs. But it was still, I think, a telling sign that the way differential equations or any class has been taught for quite some time uh, hasn't really met the needs always of the students who are taking the class. Like if they need applications that will help prepare them to be an engineer or a physicist, then that's maybe the type of stuff that we should be doing more of. And I think that the computer software has definitely gotten better. I still had the restriction of, well, even if I would have had a computer lab large enough, my college wasn't going to pay for Mathematica, wasn't going to pay for Maple. And so I thought, well, even if I take the students to the computer lab, I can't always do everything there that I would want them to do. And so I found some online ways around it, or uh, had like I did a lot of like some of the numerical uh, analysis type things in Excel, where they could uh, change some parameters on their own and see what would update. Uh, but it was difficult. And then I came across like this CD-ROM of that well, it reminded me of what the past probably looked like. And it was a CD-ROM of applets for differential equations. And I thought, this is great, except uh, it wouldn't run on the current version of Windows. And so I did everything. Like I got the Center for Teaching and Learning at my college to try to get them to open for me. And I think we finally got them open, but but then we couldn't read the files properly. And that's because I think they were in some old version of Java maybe. And so Java and Flash are problems. I mean, Flash will be gone at the end of the year, but like Java is still around. But like older versions of Java, like I wish that I could go and see what those applets look like, because it would be nice to have them for a situation maybe where I want to maybe like show a quicker demonstration maybe, and then have students play around in software later on. I don't know, like uh, it might not be nice to have them. It might not, but either way, it sort of seemed like one of those remnants from the past of how things used to be.
Yeah.
And just a reminder that we have another way through modern software that I really am surprised that there's not more widespread use, or there's not like even more introductory differential equation books like written using software that I could pick up and use with my students today. And I haven't really seen one like a textbook like that that I would feel comfortable teaching from myself. But the semio modules and scenarios, I think are a big like a step in the right direction to have everything for differential equations all in one spot in a way. And like I put a PowerPoint of something like that I did earlier that I was talking about in the chat, but I have a worksheet about it too, but I couldn't find it. But I can't say enough about what the semiote is doing, but the one thing I didn't mention before that I want to at least say something about is I have my students participate in their Scutum competition, and so I thought, well, this will be a disaster, like a 2-year college participating in a differential equations competition against Lawrence Tech and Kettering. And I thought, okay, this won't be good, because I thought like our there would be more than just like the 3 institutions involved in this competition, but it just ended up being the Lawrence Tech and Kettering and us. And so lo and behold, my students, like they got the problem, and it was about recycling trash. And so it was about like the most efficient way to sort trash. And so they took like, and I saw what the other groups did, but at the big report out, but my students, I saw them take some big fans and then like cut up like blue paper and red paper, and then blow the fans and see like how many of the red papers got sorted out. The red ones were supposed to be the things that could be recycled, but were sorted out by the different angles of blowing the fans. And there's definitely something to be said for like simulation, and whether that's like literally like putting together a simulation of things using fans and colored pieces of paper, or like simulating it using computer software that like just puts something extra to the visualization that helped the students understand what was going on. And they were the only group that ended up using any simulation at all, which was, again, a reminder that like even at Lawrence Tech and Kettering, where I'm sure that they have the ability to have students use Maple and Mathematica if they wanted to, because I'm sure they have it in their engineering classes. They're not using it in their math classes or in their differential equations classes. So this is still that reminder that that sometimes the mathematicians are behind where other departments and where industry is in using software. And so because of that, simulation, even though it wasn't a computer simulation, like my students won the competition that year and placed first place in Michigan, and they just loved it. And so this is just another thought, I guess, that I had, that even if you don't want to necessarily teach using some of these scenarios, like offering that participation in the Scudem competition as a class activity wouldn't be a bad idea, because I offered it as a class activity, and that was one of the items that the students could select from as like their project for the semester, like participate in the Scudem competition, or like pick a problem from the book and expand on the scenario, or like there were a couple of other options, but that was one thing that I found that worked, and I guess my experience with having students participate in it. Um, yeah, so I guess uh, like, and this might be for Steve, gave the indicator that you know about Silo, or even David put a note about the decimals in GeoGebra. I'm just wondering if uh, there's like a favorite scenario or a favorite applet, or just something out there that you want to try that could be interesting, because that's sort of what I'm thinking, like, because I'm at the point where like I know that I want to teach the entire course differently the next time I teach differential equations, but I don't want to necessarily like just go one route. I sort of want to um, like, I guess get a sense of what is the best that's out there right now. Uh, yeah, like just like a favorite, like, yeah. So I'm guessing I'm just more or less like looking for what a favorite application problem, or a favorite scenario, or a favorite applet, or a favorite project is that maybe uh, you found success with students in the past, or something that you wanted to try and just haven't had time to do it yet.
I haven't taught the class yet, so couldn't share anything out.
I'd say I have for the last couple of years started the class with the modeling population with the M&M toss, um, activity, a variation on that. And I find that really useful because it gets at the questions of modeling kind of real world activities, the role of randomness, the role of unusual results, but also the role of um, models that don't account for strange circumstances. So for example, it's fairly common, like in a bag of M&Ms, to have one M&M that has either no printing on either side or printing on both sides. It's actually fairly common, and you wouldn't know this until you're like going through and counting. And so this activity has them, shake up the M&Ms and then roll them like dice, or flip them like coins, I guess you could say. And that particular member of the population dies if it's M&M, if it's M facing up, and so you put it off to the side, or maybe it's they live if it's M facing up. Anyways, one of the consequences of this is when you start having the model situations, and this M just keeps surviving because it's always there. And they start asking questions like, oh, I didn't realize that this would be a problem. And so it allows you to kind of address the way we mathematically model. Sometimes doesn't account for real life weirdness. And so we have to go back and kind of fix our models and include things for that. The other thing that's nice about it is it gets at this idea of the difference equation versus a differential equation. And some of them are coming straight out of a Calc 2 context. And so sequences and series are still pretty fresh. And most of them can be on board with a difference equation. You know, the difference between a sub n and a sub n plus 1, they get that idea. And then being able to make the jump from the discrete to the continuous to talk about differential equations, that's really helpful as an intro activity. So it does kind of double duty. It allows mathematical modeling and discussions around mathematical modeling. At the same time, it also allows for that gap to be bridged between what happens in real life, which is very often we model things with discrete, you know, table data, where you start with kind of a difference equation, and then from that we make the leap to discrete or continuous data and talk about a differential equation. That's, I find, really helpful. But for me, one of the things that I've discovered my students, and maybe it's a local phenomenon, maybe not. I doubt it's local, but you know, maybe it is. My students tend to have a very difficult time with the idea of how do I explain and understand a mathematical model like a differential equation that is all just parameters. There's no numbers in there. And how do you make sense of the equation? What are the variables? What do the variables mean? What do the parameters mean? What's the range of values for parameters? I can pull up an example if you want and show you what I'm talking about. But throughout the entire course, I'm always coming back around to, here's an example of a differential equation that models blah. Let's take a look at the equation and sort of break it apart. And just the simple idea of the units of a differential equation have to make sense, and whatever's on the right hand side has to match the units of the left hand side. You would be surprised how shocked some students are at the idea that the units actually matter. And it's like, oh yeah, this is super important, especially in this class. And so if that differential equation is, you know, dr dt, and you're looking at, you know, change in radius over time, then those same units on the one side of the equation have to be the same on the other. And that becomes like a habit in my class that I start to build. And every time we run into an equation, especially one that's modeling a real life situation, we analyze the equation. We do kind of qualitative analysis on it. We do analysis of the variables and stuff. That becomes kind of second nature to them. So for their final exam, one of the things they have to do is I give them, they all get a different situation where they have to look at these differential equations that are pre-made, right? They're pre-made equations, but they're modeling real world, you know, like the SIR model for spread of a disease. And they have to analyze it and talk about this, you know, system of equations without any numbers. There's no solving it to you know, think about plugging in numbers, but it's still qualitative analysis of these equations, which is super important. And that's a skill that they have to practice because they suck at it, because we all suck at it until you do it a couple of times. Everybody sucks at it. And it takes practice and patience. And it's a really important skill to develop. So for me, that would be my big piece of advice is don't think of it as what one-off activity can I do? Think of it as how can I scaffold throughout the entire course, developing, thinking about modeling, but modeling in a very specific, structured way. If you have a model, what are the terms in the equation have to have in common in terms of units? What are they, you know, what does that parameter mean in terms of units? So I'll shut up, but that's what I would say.
No, I guess I know I absolutely agree with that, and that's sort of, I guess you said it better than what I said, because I guess that's part of what I was getting at earlier, at least trying to, when I was asking about whether it might be beneficial to have a student maybe revisit the same scenario more than once throughout the semester to build up a different techniques that they've learned and build up the problem-solving ability and build up their understanding over time. And I think that a lot of times we get to the final exam or final project, uh, and we really want to know like what has the student learned over the course of the semester. And some students might have gotten a certain concept after the second week, and some of them it may have taken the whole class, but they finally got everything that they needed to get. And so I really agree with that sentiment of the scaffolding and just helping students along and revisiting things as it's needed to really uh, uh, get the better understanding. Uh, so I'm wondering if uh, because I saw the comment, David, about the GeoGebra and Desmos activities, and I went back and I kind of poked around to see if I could find something, and it just seems like another one of these areas where the the information is just still a little disorganized. There are specific lessons that uh, a instructor has made about differential equations on Desmos, but I don't see them organized anywhere. So I'm still wondering, from that perspective, um, or even from your perspective, Stuart, if if things for you as a student would have been organized all in one place for you to find them, uh, what benefits would you think that you would have gotten from them? Or again, I really want to circle back around to that time issue again. Do you feel like it would have been a lot of extra time learning a certain software program that would have been too overwhelming on top of everything else you were being asked to do, or even from Steve, your perspective of students using software and the time for the students to overcome the learning curve of software that you've seen. So yeah, I guess anything on that type of challenge for me would be helpful to know sort of what to expect when trying to use software with
Um, I think that if we would have had to learn how to do software, I would have personally gotten a lot out of it, and I think that a lot of my class would. Um, and I think that the best implementation for that is if you're planning to have students use a certain type of software, is dedicate a specific lab hour or lab time every week where they get to practice, because that way it's part of the class and it doesn't feel like it's something extra to do. Because I know that in my statistics class, when we learned how to do R, that was covered during a lab time. And also when I was in my elementary analysis class, we learned how to use LaTeX. So we had a lab hour for LaTeX just to learn how to do it. And then I guess once students are becoming more comfortable with the software, you can kind of scale back on the lab time and have them do it more independently. But at least at first, I'd say if you're going to teach them, have them do it in as part of the class, so that it doesn't feel like it's a bunch of extra work that they have to do by themselves.
Definitely. Yeah, if you don't incorporate it into the class, it's a train wreck. And I would go even further and say it's not even about, okay, we'll have class and then we'll have lab time where you're going to learn the software. You're going to use the software in class, right? So my students, when we were meeting face to face back in the old days, when we used to teach in a classroom, oh, those were good old days. Um, my students would bring their laptops, or I would always try to schedule it in a room that had laptops available. And we have a site license for Maple. Um, the other option, as I put in the chat, was Maple, and other software companies do the same thing, will offer kind of a reduced lifespan version for students for cheap. And so I get either an OER textbook, or I get a textbook that is like 2 versions outdated. Right now I'm using a 2010 textbook that you can get online, a copy of online for like $20. So it's dirt cheap for students if they want to buy the textbook. They don't have to buy the textbook, but I make the copy of Maple, their student copy of Maple, make that their cost for the class. And so, and it's like $80, $75 for a semester access. It's actually a little bit longer than a semester access for Maple. And we use it every day in class. As long as you use it, people learn how to do it. I mean, it's like you're teaching them a skill, and you have to practice it. And so if you're doing everything in class and you never use Maple in class, then the students, big surprise, won't learn how to use it. But if you're asking them to do things, hey, take a second, let's see if we can use a numerical method to find a particular solution, for this differential equation. And they have to practice the skill right then and there. They learn it, and they learn it really fast, and they love it. It becomes much more intuitive for them to pick up the tool and use the tool for exploration. So I can't tell you how much more difficult it was to teach this class when I was not requiring students to have access to Maple on their own. And up until about 2 years ago, I would strongly encourage students to get their own copy of Maple. And then I just decided, you know what? No, you need to have your own copy of Maple. And if you want to rely on the one that's on campus, then you're just making it, you're basically putting yourself in the position of, I can only work on this stuff when I'm in a campus classroom. And that's just silly. So get rid of the textbook, or get an old version of the textbook. They're not that different. And get a couple of versions old textbook, and use that, and have them spend their money on the important stuff, which is the software. And it doesn't matter what software, whether it's Maple, Mathematica, MATLAB. um, God, what's the other one? I'm drawing a blank here. Doesn't matter what it is, as long as they're using it. Because once they use one, they learn how to think in a moderately programming way, and they learn how to exploit it. Then picking up any other program becomes a dream. So Stewart, you know something about using R. And so the first time you sit down and somebody goes, hey, can you do this in Mathematica? You're like, well, I've never used Mathematica. I guarantee you it's going to take you like a quarter of the time to learn how to use Mathematica, because you already know how to do stuff in R. And then the third language that you start playing around with, it'll be much easier to use. So.
Well, like I had to, prior to learning R, I had to take a computer science class that dabbled in C++,
Yeah.
like for my degree, and it made learning R a lot easier because, like you said, I knew how to like, I guess, like code it a little bit, so it helped me out. And like I like that you make it a requirement to have the software, because that would be nice, because my experience has been like, a lot of times in earlier classes, they neglect to teach us anything with software, even though that can be important no matter like what discipline you're going to be in. And then later on, they expect that you know the software, but no one's ever shown you before. So it's like, well, I guess if I want to do this, I'm going to learn it on my own, or just kind of miss out on the opportunity.
That's the dirty little secret that used to be statistics for a long time. 25 years ago, that's the way statistics was. You'd show up in your advanced physics class and they'd be like, okay, so let's take a look at the standard error for this laboratory experiment. And you're like, whoa, what? What's that? And nobody ever taught me that. And they're like, well, you learned it in math, I'm sure. And you're like, no, you never taught that in math. And they just assumed everybody had experience with statistics. And now they start requiring more statistics. But now the problem is with computer programs. And so they think, oh, well, you know how to, do this stuff in a computer program. And you're like, no, if you don't ever use it in your lower level math classes. Right now I'm pushing really hard to get our calculus sequence, the entire calculus sequence, to just start using this. And the scary thing, and that gives us hives and keeps us up at night, is, oh my God, if they learn how easy it is to take the first derivative of a function, will they ever forgive us, for making it seem difficult in class? And the answer is, yeah, as long as you don't make it only about doing it the tedious long way. You show the progression and you use the tools for all the cool stuff that they can do.
Well, like
And
I definitely think that it's useful to know how to do it by hand, but in just like you've said before, for them it's a lot more intuitive to just see it, like to see it happening, and to like be able to plug it into a model, like a computer program like that, and witness what happens like in real time, so to speak. It makes it a lot nicer to see, because I know like when we got to like witness the like programming stuff happening in my differential equations class, is like, oh, that makes so much more sense now. Like it would have been nice to do it the whole time, but we kind of just had to do everything by hand, and that's kind of like how I've been. But now that like I like just for fun was like looking into jobs I could get with a math degree, like a bachelor's in math. And like a lot of them are like bachelor's in math, plus you have to know all these coding languages. I'm like, I don't know how to do any of, or I only had to do like one or two of these, not all five, because they've never told us this before.
Yep.
So it just would have been
and
nice
you know
to
what?
know.
Those employers, if you went in and said, I know how to do one of them pretty well, they'd be like, that's cool. We can teach you.
Yeah.
If you know how to do one of them pretty well, we can teach you some of the other stuff that you might know how to do.
Yeah.
But if you've never used any of them and you don't know how to, solve problems using these tools, I mean, it's like the old days with when graphing calculators first really started hitting. People just did not know what to make of these things.
Yeah.
But students started using them, and the next thing you know, teachers were like, "Oh my gosh, we can do stuff with them in class. It's amazing."
Yeah.
Well, yeah, and I guess your point about like statistics is very clear, because I I've been I think about this a lot. Like we're at the time now where, like at a lot of colleges, like a statistical literacy class is an option compared to like the traditional algebra-based statistics class. And so I really think that we will eventually get to a point where there's a similar track for calculus, where like visualizing calculus or just thinking about calculus is like a class where you don't have to get into the nitty gritty theoretical like things that you might need to be a pure mathematician, but like just the calculus that you will need, and how to visualize the graphs of the derivatives, and how they relate to each other. Like I can't ask those types of questions as an exam question a lot of times, because I want to make sure that the students are ready for what will be on the departmental final exam. And so I don't think that we're at that point yet where like if I show the students the graphs of a function and its derivatives, or ask the students to generate those graphs on their own, that the students necessarily feel like they're getting a lot of value out of it, because they know and I know that that's not what they're going to be asked to do on the final exam. And so I think that I know that on the final exam the questions are more like find the the second derivative, or like if this is the function, what is the graph of the second derivative? Or, but they're not like like questions like that are getting at the connections between, like the physical connections between the two, and like talking about like what would the units be on the axes of these graphs of the derivatives. And those are the things I want students to know and understand, but they're not the types of things that are tested on the departmental final exam. And so like I hope that we get there one day, especially since I see the change that's happened in statistics, especially. But I I just don't know like how to necessarily always motivate that sort of insight in the in the students, get them to realize like, hey, like I really uh, do need to know like what the meaning of these graphs of the derivatives are, or what the meaning of the variables are. And I guess uh, like about the calculator specifically, like if you try to find find the numerical derivative using the TI-84, like sometimes it will say that it's 0 when it's really undefined. And then I sort of was like, okay, this is not right. But I figure out why the calculator was doing that, and why like certain times finding the derivative like has to be done like by hand, because it just a derivative that you can't find numerically, because the calculator is going to spit out 0. And so if you know that like what a critical number is, and you know that you're trying to find the derivative at that point, then you will know, well, then I have the tool to find the limit by hand and evaluate that derivative by hand. But then otherwise, like if I like know that like the critical number is like a certain if I know what the critical number is, I know that there's no issue at that number, then I can go and use the numerical derivative in any anything like that in the calculator, or the computer program isn't going to give me an issue. So like I think that that's where I want my students to um, be, like not like I have to know how to calculate the limit by hand because I'm going to need to for the final exam. I want them to know like I might need to know how to use find the limit to uh, uh, because certain times I'll have to use the limit if there's an issue that I can't calculate something using the computer. So um, anyway, that's just my rant, given that I finally like have this whole document about how the TI-84 actually comes up with those weird issues that they use, like the symmetric derivative, and like which is like recursive differences of derivatives and things along that line. And I have my students read through the 2-page handout that I wrote about it, just so that they're aware of the fact that this is the reason why I'm showing them how to find the derivative using the limit process. Because if you see this issue arise, um, you won't be able to find the limit using the calculator. And so at least I hope that I planted the seed in them that this is a reference for me to look at, so I know if I'm in one of those situations where I may need to find this by hand.
boundary value problems, right? That's essentially what we're talking about. And if you're designing your curriculum around boundary value problems, and I don't mean that in a differential equation sense, but if you're designing your curriculum around what do you do in those weird moments when, then I mean it's interesting, but the vast majority of the time that they're ever going to use, you know, any kind of calculus concepts, it's not going to be at those boundary value problems. It's just not. And there are other, workarounds. Instead of, freaking out that you can't evaluate exactly when x equals 2, you could use another concept in calculus and say, well, what happens when x equals 1.99 and 2.01? And then you have some idea what's going on just on either side. So I would be thrilled if a student of mine approached the problem kind of creatively and said, I don't want to have to do that. The limit definition, I don't want to do that. I'll use the calculator to just kind of look really close on either side and let it kind of play around with it that way. I'd be thrilled if one of my students came up with that. Of course, I think they're probably just as likely to come up with that as they are to revert to the dreaded limit definition of the derivative. But still.
Oh yeah, no, I actually, I think it's funny that you said that, because one semester in my Calc 1 class, like I'm never really, I guess I'm not, I've never been very strict on like how a student evaluates a limit. Like, so I had one lady one time, every single limit she evaluated numerically and gave me her table, and then I I mean, she was actually the only student who got all of them right too. And so, like, I just was like thrilled, and I told her, like, I appreciated her approach to some of the problems, because it's a situation where I know what students who wouldn't have used that approach usually end up doing. Like I get like the sign of 5 theta over theta. Like that's
Theta.
one of them where I get lots of wrong stuff all the time. And so this numerically, and so I loved it. And so just like getting our students to like see things differently, I think is very important. And I think that the idea of using projects is one of the ways to get students to think about things differently, and not just as it's a problem to solve in a textbook.
David, I'm curious, have you started looking at textbooks as, if you're thinking about teaching the class in the future, have you started looking at, or is there a textbook that they use over there that you're looking forward to, either looking forward to or not looking forward to using? I'm curious.
So the book that my school uses right now, it's the Nagel Saf Snyder book. The one that I used when I was in college, I think it was the ZIL book. They typically, what happens is, if there's like a new edition of the textbook that comes out, we'll look at upgrading or possibly changing it. One of the things that we do have as a school policy, we don't have to adopt open resources, but we do have to consider them when we do consider changing books or whatever. In some cases we just upgrade to the next edition, but we do take a good hard look at what's out there. The problem is, I think there's only, in my department, I think there's only 3 teachers that have really taught the class and consistently. I want to teach it at some point, but there's just always something going on, chairing a committee or whatever, and so it's like I can't take a new class on right now. But yeah, so right now, to my knowledge, they're not currently upset with the textbook, so I don't there's no rumblings about them changing it. If they do, we usually do like a subcommittee, and I would, definitely be interested in looking at textbooks, but not right now. So yeah.
Yeah, well, okay. So I guess I was going to say something because you mentioned the Zoll book, and that's what my college uses. Uh, well, that's what I have been using because that's what my college uh, uses. But I think that the next time I teach the class, I'm probably actually, uh, and I got this idea from one of the instructors that I had in college myself, but he used the Schwam's outlines for every class that he taught. So I'm probably going to go with the Schwam's outline for differential equations. That's like $17.99 on Amazon, or and and call it a day, and supplement with the some of the semi-ode scenarios, supplement with a, a like lab projects, and I think that that's perfect because as a student I liked learning from the Schwam's outlines because it was like, here's a little brief summary, here are the like some sample problems and some answers, and then here are some problems with the answers in the back of the book. And so it was enough for me to have, like, it was really all I had time to do in terms of reading, in addition to like reviewing the lecture notes, in addition to doing the project that the instructor gave. And so I don't think it's a bad option, and it's a lot cheaper for the students. And so outline, I'm definitely going to go with an OER textbook or an old edition of some other book, because I do that for my calculus class, and it's only like $5. So I think that we're in the times where the more important thing is like making sure that the students will have uh, the the deeper understanding, and that goes beyond the textbook knowledge. And so if that's what I want students to have, then why am I still using the textbook as the primary uh, tool for them getting the information outside the class, and not the exploration through computer uh, simulation. So anyway, that's what I thought of when you mentioned the Zoll book.
Yeah, that's what I used in college too. So I put a link in the chat. There's an online book that I happened to come across. I don't know if that's, if you're teaching it. Again, it could be a supplementary resource. I don't know. The Octave link that I sent out earlier too, the software that's free also. So, you can have students download that as well.
Yeah, so I guess I know that we're close to the end of our time supposedly together today, but Stewart, did you want to make any last comments about anything that related to uh, like the overall discussion, just to wrap us up here?
I don't know. I think we kind of covered everything. I'm like glad that the discussion like happened and built on my little presentation, because like I definitely feel like I have a lot of ideas now. No matter what class I end up teaching on, within the next few years. And like I have a lot of ideas of what I can do to incorporate some software and just some projects and stuff to keep students engaged and also give them some real life context behind the mathematics. So I appreciate it a lot. Because I'm trying to take all the insight and help I can get before I start actually having to teach.
Yeah, all right. Well, yeah, well, thank you for all of you for being here. I'm going to just stop the recording